Welcome to the Knowledge Graph seminar. Today, we are in the week 5 of the course. And in the course until now, we've talked about what is a knowledge graph. We have defined the knowledge graph, its data model, and some query languages. And for the last couple of weeks, we've been talking about how to create a knowledge graph. And in that process, we talked about how to design the schema of a knowledge graph. Last week, we talked about how we can create a knowledge graph from structured data. And the focus for this week is going to be how we can create a knowledge graph from text and images. Today's lecture is going to primarily focus on how we create the knowledge graph from text. But in the lecture on Thursday, we would also hear about how we can create knowledge graphs from images. For today's lecture, I have structured it into two parts. The first part is going to focus on the methods, which is going to be focusing on the techniques for creating knowledge graphs from text, mostly in abstract. And in the second part of the lecture, I will talk about a very concrete application where we can take those methods and try to apply it to a real world problem, so that you can see how the techniques work in practice. Okay, so we start with the first part. We will talk about the methods for creating a knowledge graph from text. I will start by giving a little overview of the problem. Then we will talk about a general technique called language models, which can be used both for entity extraction and relation extraction tasks. And then I'll conclude this segment with a summary. As we all know, a lot of useful information is available in unstructured text. This can include things like SEC filings, Wall Street Journal, and financial news. If there is a way for us to automatically process this information and construct a knowledge graph, we can do a lot of interesting analytics on that. And an obvious technique for doing this kind of processing comes from the field of natural language processing, and in particular from information extraction. But at the outset, I want to make it clear that today's lecture is not a lecture on NLP, and it's not going to be any in-depth discussion on NLP. Our focus and the focus of this course is on knowledge graphs. Like, how do we construct structured, human understandable representations of a certain part of the world on which we can do inference and on which we can do analytics. And for the purpose of this lecture and for this course, we are assuming that we can use NLP as a black box. It's like a tool that is available to us that we can apply to a given problem towards the goal of creating a knowledge graph. And I cannot stress this point enough, because NLP and the techniques that I'm using, they are covered in a full-length course somewhere else in the curriculum. And I'm not trying to reproduce or redo that. I'm just trying to leverage what is available to us in the context of the primary goal of this course. In the first lecture, I had shown this slide where we talked about how we can extract information from sentences and represent them in a knowledge graph. So, for example, given this sentence, Albert Einstein was a German-born theoretical physicist who developed the theory of relativity. We will extract entities such as Albert Einstein, Germany, theoretical physicists, etc. And then we will extract relations such as born in, occupation, and developed. And we can connect them using this directed graph representation. And once we have the directed graph representation, we can do additional inferences using that information, such as theory of relativity is a branch of physics, and theoretical physicist is a kind of physicist, etc. Okay, now, but in the overall scope of extracting information from text, we have the problem of entity extraction and relation extraction, like I just described. But there's also the problem of entity resolution. And by entity resolution, what we mean is that the same entity can be referenced in a text in many different ways. For example, we may have a person, John Smith, and in the text, we may refer to it by he or the company president, or there may be other ways to refer to the same real world entity. I'm not going to cover entity resolution in this lecture, partly because I want to limit the scope, and partly what I found in my personal experience is that right now the entity extraction and relation extraction tasks are hard enough to do very well on complicated problems that the focus is not yet on entity resolution. We are still trying to do well on these two primitive tasks. And for both of these tasks, the current fashionable or current trend is to use techniques called language models. And so I'll start by describing at a very high level what a language model is and how, and then when I describe the techniques for entity extraction and relation extraction, I will discuss how language models are currently being used in that process. So the overall concept behind a language model is that it's a tool or it's a model that predicts what word should come in the text in a sequence of words. So for example, if you're given a text fragments, students open their ... The task for a language model is to fill in the ... as to what could be the next word. For example, in this sentence fragment, we could have students open their books or laptops or exams or whatever else. And with each predicted word, it is going to associate a probability of likelihood with which that word might come next. So more formally, a language model can be also viewed as a probability distribution such that given a set of words x1 through xn minus 1, we want to predict the next word xn given that we've already seen x1 through xn minus 1 in our input. Okay. Now, language models are used all over the place. They have lots of applications. We go and type in a query in the search engine and it gives us likely completions. So underneath it is basically using a language model to perform the task. Similarly, when we are on iPhone and we are typing a message, at the bottom or just above the keyboard, it is suggesting the likely next words. So it's a pretty straightforward application of the language model that we see on a daily basis. These language models these days are created using deep learning models, and recurrent neural networks is a popular approach for creating those language models. There are several variations of these pre-trained language models that are available, and those variations, they depend based on what data you use for training, whether it's a single direction versus bidirectional model, which particular neural network architecture you're using. And as I have noted previously, I'm assuming for this course that a language model is available to us off the shelf, and we can adapt it for the task that we have at our hand, which is the task is to create a knowledge graph, right? Now, it may be interesting to actually say a little bit more about the difference between a single direction versus a bidirectional language model. The example that I gave was a single directional language model in which we are given a sequence of words and we are predicting the next word. In a bidirectional model, we are given a complete sentence in which one particular word is omitted. And now we have information both to the left and the right of the word, and we are predicting the word in the middle. So it's useful to understand this at a very high level in terms of what these models do and what they have been trained to do. A popular language model which has gained a lot of attention in the last few years is known as BERT. This was originally developed at Google, and more recently there has been a lot of press and news about a new language model called GPT-3. Okay, now let's put our heads down and we focus on the specific problem of entity extraction. I will start by giving a running example for this problem, and then I will outline various approaches for doing entity extraction, and then discuss the challenges that arise in using automated entity extraction. So take this sentence. Cecilia Love, 52, a retired police investigator who lives in Massachusetts, said she paid around $370 a ticket with tax for nonstop United Airlines flight to Sacramento from Boston for her niece's high school graduation in June 2020. Okay, so we're given this sentence, and from this sentence, we want to extract named entities, which are defined as things like places, companies, and people. And the definition of entities here is generally broadened to include things like dates, times, and numerical expressions. So, for example, here, $370, it's a number that would be considered an entity. June 2020 would also be considered an entity. It's a time. So, given the sentence above, the task is to produce an annotated version of the sentence of the type shown here. So here, Cecilia Love, we have labeled by person. New Jersey, we have labeled as location. $370, we've labeled as money. United Airlines, we've labeled as organization, and so on. Okay, so the task is to go from this input sentence shown as above to the labeled version, which is shown below. And typically, we define a set of tags to mark the entities in a sentence. Because entities can be more than one word, there are these 5 tags which are defined to mark the boundaries, where B denotes the first word in the entity, E denotes the last word in the entity, I denotes the internal word in the entity, O is a word not in the entity, and S is the single word entity. So given the sentence that we were looking at previously, for Cecilia Love, Cecilia would be marked by B and Love would be marked by E. And the rest of the words, we can see that they would be tagged in an identical manner. Now, in terms of broad approaches, there are 3 broad approaches for extracting entities. There is sequence labeling, the neural models. By neural models, I actually just mean language models, and the rule-based approaches. And I'll give a quick overview of each of these approaches. In the sequence labeling approach, we take a standard machine learning type algorithm, such as conditional random field, and we give it training data, which uses features such as part of speech. So for example, we may give it an input sentence and we might identify part of speech for every input sentence and say that, okay, if it is a noun, then it must be a named entity. The training could also be based on whether a particular phrase is present in a master list of named entities. Word embeddings, which we discussed in the first lecture, could also be used as a training feature. The prefix of a word, and whether something is in a appears in a all caps notation. So as you can tell, if you're going to use any kind of machine learning approach, in this case, a significant feature engineering is required, because it's not clear which features we should put in, but there is a lot of wisdom and a lot of practice available using which we can choose what features we should be using in an entity extractor. Now, let's now talk about the use of neural models for entity extraction. So here we are going to take an off-the-shelf language model such as BERT, and we are going to apply it to our problem at hand. And there are two kinds of steps that are involved in doing that. First is task independent training, and the second is the task dependent training. So these language models that we are going to get from off the shelf, they are trained on very broad corpus. So maybe all the news or some very general purpose corpus such as Wikipedia. But in general, we are always interested in a particular domain or solving a particular problem. So if we are interested in extracting entities from financial documents or legal documents, the step of task independent training is to retrain the model that we have on the domain that we are interested in, okay? So that it understands the peculiarities or the vocabulary or the words that appear in that particular domain. So that's the first step. And the second step is the task dependent training. So in this case, the task is entity extraction. So the next thing we are going to have to do is to train our model on the task of entity extraction. And the way this is done is we will take our sentence, and in our sentence, we will introduce special markers. So the sentence we were previously working with, here we have a marker called CLS, which denotes the beginning of the entity, and SAP, which denotes the ending of the entity. These labels are pretty arbitrary. We could have put any marker here, but CLS here is, I think, short form for classification, and SAP is the short form for separator. Now, when we train a language model in which the sentences have these markers, what it will learn is how to predict these markers, okay? We can repurpose the language model to this entity extraction task by now asking it to predict whether the next token is going to be CLS or whether the next token is going to be SCP, right? And if we get it to predict these distinguished tokens, we know where the entity boundaries are, and we can use that information to mark where the entities are in our sentence. So it's a pretty clever way of just taking a very general purpose language model technology and repurposing it to entity extraction task. Okay, let's now talk about rule-based entity extraction. The basic idea here is that we are going to write a set of rules which will tell us how we should extract the entities. And these rules can be based on either something very simple as regular expressions, or it could be looking up things in a dictionary, or it could be invoking custom extractors, okay? But the bottom line is, again, just like in feature engineering, we had to come up with features. Here, we have to do rule engineering. We have to have enough understanding of our domain to figure out what the entities are, and we have to be able to specify the relevant rules which will help extract the entities. Okay, so that was sort of my quick overview of the methods one can use. The difficulties that arise in doing entity extraction well are, one, obviously, is ambiguity. We can have entities such as Louis Vuitton, which can either refer to a company or to a person or to a product. So in cases like this, it's difficult to figure out what should be the appropriate label for that entity. Training data or feature engineering, or rule engineering, all of that is the bottleneck in doing this process well. There are domains where there are variations which are very peculiar to that domain. So for example, if we are doing extraction in biology, you may have entities such as duplication of cell by fission, which is like a long phrase, which is very different from the kind of things we were seeing in the example where we were primarily limited to company and organization and location, etc. And in some domains, you have to extract very general terms as entities, like attach or bind or synthesis. And there again, it becomes a challenge how you define your rules and training to do extraction for those very general entities. And finally, entities have multiple forms. So these forms may include singular versus plural. You may have abbreviations for an entity. You may have morphological variations of an entity. All of those things are going to appear in the text, and we won't be able to figure out that they are all referring to the same entity unless we have a lot of lexical knowledge. And if we really wanted very high performance on the entity extractor, we also need a very good lexicon for the domain so that we can accurately distinguish whether different variations of an entity are actually referring to the same thing. All right, so that was my quick overview of term extraction. And now I'm going to move on to methods for relation extraction. And here again, I'm going to begin by giving giving one example of the extraction task we want to perform. Then I'll give a broad picture for various techniques for doing relation extraction, and then talk about what's hard, what is difficult about doing relation extraction. So the example is the same sentence that we considered for entity extraction. And now we want to extract information such as Cecilia Love lives in Massachusetts, where lives in is the relationship. United Airlines flies from Boston, United Airlines flies to Boston. So those, we want to extract those relations from this sentence. Okay, so actually I have multiple examples, not just one example. One very popular task that a lot of people focus on is to extract information from Wikipedia, because it's very useful for enhancing the search results. A lot of the fact extraction from Wikipedia is straightforward, but there are a lot of corner cases. So if you look at the Wikipedia page for Larry King, he has been married multiple times, 6 or 7 times. And for each of his marriages, there is time duration, right? And if a person is married only a single time, then it's pretty straightforward to extract the spouse relationship. But now the person is married multiple times, and there is time, and sometimes he was married to the same person twice, right? So it becomes very complicated very soon to associate appropriate temporal information with the fact that you are extracting. I mentioned domain-specific extraction when I was talking about entities, but the same thing arises for relations also. There are domain-specific extraction systems, for example, for the medical domain, where they are primarily interested in information such as what things cause what disease, what drug can treat what symptoms, what kind of enzyme or chemical disrupts what kind of process. And that's those meanings and the way they are defined is very specific and peculiar to the biology domain. And that by itself becomes a whole subfield within relation extraction. Even for relation extraction, there are 3 broad approaches. There is a rule-based approach, there is a supervised learning approach, and then there is open information extraction. Even within supervised learning, people make a lot of sub-distinctions, whether it is semi-supervised or fully supervised, but as long as the approach is supervised, for the purpose of my discussion, I have kept everything under the same heading of supervised approaches. The open information extraction approach is a way of extracting information where they don't give any specific attention to the meaning of the labels. They just extract triples out of text. So just as an example, if you're given a sentence, Dante passed away in Ravenna, the open information extraction approach will simply take this text fragment and they will turn this into a triple, which is shown here to the left. Dante passed away in Ravenna. As opposed to taking this text and populating a knowledge graph in which we have a vocabulary of relations which have well-defined semantics. So on the right, I'm showing a little property graph where we have a person node and there's a city node, and there is a relation called depth place, which probably has some domain and range constraints defined for it. It has some rules and constraints on what values it can or cannot take. And whenever we are going to talk about where a person died, we would use the same relation. Okay, so there is that careful knowledge engineering and knowledge representation that has happened, which would be not done in the case of open information extraction. In open information extraction, you just process text in a completely unsupervised way. It's a popular and a very compelling story for certain kinds of problems, but it becomes very difficult to do the inference and analytics using the information we will extract in an open information extraction way. So for the purpose of my lecture here, I have decided to keep that outside the scope because we are primarily focused on knowledge graphs, and we are interested in techniques which will help us populate a knowledge graph where we have well-defined meanings for the nodes and labels in our representation. So for the rest of my discussion, I'm going to primarily discuss information extraction or relation extraction based on syntactic patterns and supervised learning. Okay, so syntactic patterns, they were originally introduced by Marty Hurst, and in her honor, they are also referred to as Hurst patterns. And I'll illustrate that using an example that I took from the original paper on this topic. So let's take this sentence. The bow lute, such as Bambara and Dang, is plucked and has an individual curved neck for each string. Now, I've never seen a bow lute. I don't know what Bambara and Dang is. These are the words I may be encountering for the first time. But we can, just from the syntactic structure of the sentence, we can say that, well, you know, Bambara and Dang must be a kind of a bow lute, assuming kind of or superclass is one relationship that we are interested in. So this was the key insight that Marty Hurst had, and she said that, well, you know, we can define such syntactic patterns which, based on the way a sentence is structured, could give us very strong indication for what might be the relationship between them. And she had, in her original paper, she had several examples. So for example, if we have a sentence such as work by authors such as Herrick, Goldsmith, and blah, 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 we know that Herrick and Goldsmith, they are authors, right? And then if you have a sentence, bruises, wounds, broken bones, or other injuries, then we know that in this sentence, bruises and wounds must be kind of injuries, and so on and so forth. So you can follow the rest of the examples in the same way. Now, when this idea was originally introduced, you know, people thought, oh, wow, this is really cool. And if you can do the extraction like this, wouldn't this be really a very scalable way of doing it? But it turns out it's not that easy to generalize. And so even in the original paper, you know, there was this section on, okay, how do you generalize it to relations that you have not seen? And the general methodology that was suggested was that, well, if you want to extract a certain relation, what you do is you collect lots and lots of examples of sentences where that relation is described. And from there, you try to figure out what are the general patterns. And then for those general patterns, you define the syntactic rules. Now, if you take some relationship such as has-part, it's been very difficult to find very general patterns about how you would extract it from the text. And I will actually give you more examples of this in the second part of my lecture. Some people have Some people have undertaken research to see if they could automatically learn these patterns instead of having to manually engineer these patterns using examples and working backwards from example instances of these relations and sentences. Can we somehow automatically learn them? And that also has limited success. I mean, there is some success in limited domains, but not in a sort of very general purpose manner. Okay, now let's switch to the supervised learning approach for relation extraction. And first and foremost, it requires a huge amount of training data. You may not be required to define patterns for the example occurrence of a relation is in a sentence, but you still have to find those sentences where those relations occur. And some people, what they do is they would use the Marty-Hurst style syntactic patterns, and they would use those patterns to generate lots and lots of training data, right, in the opposite direction. Given that these training data, these syntactic patterns, they are not very general and they don't always work, there is this recent idea called approximate labeling, and this is something which Chris Ray in our department here has pioneered. And the basic idea there is that, well, we can't come up with a clear way to figure out whether a particular relation exists in a sentence or not. So we are going to have lots and lots of different syntactic patterns, which might suggest that this relationship might exist in a sentence. And then we are going to use all of them. And then through a training process, we are going to learn how good each of these is, and we are going to combine the input or the signal that they give us into what we are going to feed into our learning algorithm. So as a concrete example, let's say we have a relationship has part. We want to learn this from the syntactic structure of the sentence. Now, if our weak labeling function could be that if in a sentence we have A has B or A have B, then we could say that, this might be suggesting that A has part B. And we know this is not correct. This is not always correct. In some cases, this is correct. But that is a labeling function, a weak labeling function that we can use in our training algorithm, which eventually, based on experience, would get better. Okay. Next, let's talk about how we can adapt a language model for the task of relation extraction. And the basic idea here is not very different from the kind of trick we used for entity extraction. So essentially what we do is we take our input sentences and we put these special markers in our sentence which denote the beginning and end of each term. So term one start and term one end, that denotes the first entity, and term two start and term two end denotes the second entity. And in our training data, what we are going to train our language model to do is that when the language model encounters a sentence like this, its output should be lives in, which is the relationship that we are trying to predict. So again, the basic idea remains the same. Enhance your input data to add markers which correspond to the task you're trying to perform. Throw lots and lots of data at the model and get it to learn the output you're trying to produce. The challenges you can expect in this case are, the first and foremost is the training data. Like, how do you get lots and lots of examples of the relations of the training data which are required for this, any of these techniques to work? And given that all of these techniques are approximate. I mean, they are not going to work in all the cases. We still need human verification at the end. If the end goal is to come up with a highly accurate knowledge graph, you have to have a human in the loop. And I primarily here talked about relation extraction for entities, but there are specialized methods when you are trying to extract relationships for events, or when you're trying to extract temporal information about entities. I've not covered them in this lecture, but I just wanted people to be aware that there is more to it than what I've just covered here. Okay, so that sort of brings me to the summary of the first part, or the methods part of what I was going to say. And that is entity extraction and relation extraction are fundamental problems if we want to create knowledge graphs from text. And the overall landscape of methods is that people still prefer to use learning-based approaches for doing so, but the rule-based approaches and syntactic patterns, they are very powerful paradigms. And people are leveraging them to create or bootstrap the training data that they need for their learning algorithm. We are still trying, the state of the art is still such that we are still trying to do well on entity extraction and relation extraction. And entity resolution, I mean, that's an extremely difficult problem. Again, I kept that out of this lecture just to sort of keep the scope. But eventually, I think once the entity extraction and relation extraction becomes well tackled, entity resolution is going to be increasingly important. Okay. Now, I would like now to move to the second part of the lecture, which is going to focus on a concrete application where I can illustrate how these methods actually worked in a particular project that I was involved in. I'll take a quick scan at the questions just to see whether there is anything I should address now versus addressing at the end of the lecture. Okay, yeah, I think we'll take these questions at the end of the lecture as we get into the discussion part. Okay, so in the discussion, I'm going to talk about an application called Intelligent Textbook, where we are trying to create a knowledge graph from textbooks, and I will show how some of the techniques that I talked about we were able to apply and how well they worked for our project. So I'll start off by discussing what is an intelligent textbook, what kind of knowledge graph do we actually need for an intelligent textbook, and then how do we extract entities, how do we extract relations, and then sort of tell you about what were the experiences, how much did we succeed, and what I think is the way forward for using automatic extraction methods in service of knowledge graph construction. So I like to define an intelligent textbook as a traditional textbook, which is enhanced by a knowledge graph of concepts and relations which are found in the book. Okay, and once we combine this traditional book with a knowledge graph, I'm calling that an intelligent textbook. Now, there could be other definitions for an intelligent textbook, but that's sort of how I've defined it for the purpose of this lecture. Now, the first question that arises here is, who needs it? Why should you even care? And what problem are we solving in creating an intelligent textbook? So I think an intelligent textbook of the sort we have been thinking about is useful for making it easy for students to learn complex new concepts. And an example student for who has such a problem is a first-year student in a college-level biology. And if you talk to these students who have aspirations to become doctors someday. And when they walk into their biology classrooms, we hand them these thick textbooks, and they have to master those books if they are going to progress with their education. And the sentiment which is shared by these students is that biology is very complex, it has huge amounts of new words, and they feel lost. Okay. To help students like this, we think an intelligent textbook could be a powerful technology. And we have built a concrete prototype of what such a textbook might look like. And I'm going to give you a demonstration of this book so that you can see for yourself concretely what I'm talking about. Okay, so it has 5 different capabilities that help students. The first is that for any difficult words that appear, such as proteins, polysaccharides, and nucleic acids, student can get a quick definition by simply clicking on it. Second, it helps cross-link content coming from different parts of the book, including diagrams, regardless of which chapter those diagrams might be defined in. Third, it gives a visualization, knowledge graph visualization for every single concept in the book. And the student can interactively explore this visualization to ensure that they've learned what they were studying. Fourth, as the student is reading a book and they highlight a passage, it asks the student questions. And for example, in this case, the student kind of remembers that hemoglobins carry oxygen, but they're not sure. So they decide to touch on that question. And by comparing their answer with the answer returned by the book, they have this renewed confidence that they actually understood the material. So it's a great self-testing device. And finally, they can ask questions from the book. For example, here, the student is asking, compare protein with a polysaccharide. And in response to such a question, the book will systematically compare these 2 concepts and present the results in a nicely organized table. Okay. So using these 5 new capabilities, which are powered by a knowledge graph, the student is able to more effectively interact and engage with this complicated body of knowledge. Okay, so that was the demonstration, just to make it concrete for you how the knowledge graph is actually being used in the context of a textbook. It's actually not just a demo, it's actually a working prototype, and we have tested it out in multiple classrooms at some community colleges, at a college campus in Sweden, and also at Harvard University. And we found that these features that I just showed in the demonstration, they are uniformly liked by students. They also lead to better learning outcomes, and it also helps underperforming students. Okay, so the real challenge in creating intelligent textbooks like this is to actually build the graph. How do we actually build the graph in a scalable manner for lots and lots of books? Now, the next thing one could ask here is, okay, what kind of knowledge graph is actually needed? Okay, what is it that we are trying to create which would enable the kind of demonstration that I just showed? So let's now look at it a little bit more carefully, because this example is more different from the Cecilia Love example, which I was considering in the first part of the lecture. So let's take this sentence such as, on the outer surface of the plasma membrane, carbohydrate side chains are found attached to proteins and lipids. Okay, so that's the sentence. And from this, we want to construct a graph of the sort shown to the right, where we do have things like plasma membrane, carbohydrate side chain, those things appear in the graph. But the protein and lipids, instead of appearing as protein and lipids, they appear as glycoproteins and glycolipids, which are more special kinds of proteins. Now, those proteins were not explicitly mentioned in this sentence, right? They were probably mentioned in some other part of the textbook where they were talking about these more special kind of proteins. But when we extract information and we want to construct this knowledge graph, we want to construct this sort of cohesive global knowledge graph. And in this case, to build something like this, we would also have to resolve this lipid entity with the glycolipid entity, which already is there in the graph. Similarly, protein entity with a glycoprotein entity. Okay. Now, I think the other thing which needs to be pointed out here is what is the actual meaning of this graph? I mean, sure, this is a directly labeled graph of the sort that we've defined in this course, but what exactly is this graph saying? Now, if I was reading the logical meaning of this graph, it's kind of saying that for every plasma membrane, there is a glycoprotein, there is a carbohydrate side chain, such that that side chain is a part of glycoprotein. Okay, so I'm reading this leftmost part of the path that you are seeing on the screen. Now, the first thing you would notice here is that the nodes that we have in the knowledge graph here are generics, right? They are not things like Cecilia Love or Boston or United Airlines. These are the kind of things that we saw in the first part of the talk. But here we have classes of objects like plasma membranes, glycoproteins, carbohydrates, etc. So the actual meaning and what we want to do with this graph, strictly speaking, is much more than what a knowledge graph between real world entities is, because there is some quantification and some more background inference which goes with it. Now, we know that getting all that meaning is even more difficult. And I think when we were looking at this problem, we said, okay, why don't we see if we can just ignore that, all that complicated or background quantifications and those meanings. Let's see if we can even just extract these relations between them. Let's just extract these isolated relations, okay? So that we're still within the sort of narrow version of a knowledge graph, and we're not trying to do more difficult or much harder portion of assembling a coherent graph from the book. Let's just see if we can get these isolated micro fragments of a knowledge graph. Now, the other part of the problem is the semantic meanings, right? So we are using here relations such as has part and has function, and again, these are not as cleanly defined as United Airlines is flying from Boston to Sacramento. There the definitions are very clear, but here getting formal definitions, it's a challenge in itself. It's a problem in itself. And it turns out that, at least for this project, the biologists we were working with, they're not used to doing formal definitions. They've never even thought about coming up with formal definitions for these concepts. Now, just to sort of make it more concrete for you on the problem and the challenge that we faced is, let's see, how biologists define has part and has function. They actually like to refer to it as structure and function, right? And if you talk to biologists, you get a definition like this. Structure and function are correlated at all levels of biological organization. The form fits function. And they would say that, well, the birds have these wings which are aerodynamically shaped and they help them fly. And that's how sort of we think about structure and function. Or if you have bones have honeycomb structure, and this honeycomb structure gives the bones strength, but it also keeps them light, right? And so that's sort of what you get. That's sort of what we got when we were talking to biologists about, okay, give us the meaning of structure and function. So this by itself, we didn't think it was very useful from a computational point of view. So we said, okay, well, is there a way we can approach this problem from a computational point of view? And I think the way we like to think about this in the context of the design of knowledge graphs is to think in terms of competency questions, right? Can we come up with a set of questions that our knowledge graph should be able to answer? And could we work backwards from there to define what should be the meaning of the nodes and edges? And so we came up with two broad categories of questions: diagnostic questions and educationally useful questions. And I'll give you examples of each of these categories of questions. So diagnostic questions are questions which basically test whether the system has the knowledge, the basic knowledge. So if you ask the system a question such as what is the structure of X and what is the function of X, the system must be able to answer it, right? If the system cannot answer that, then it doesn't even know what a structure and function is, then what else can you expect it to do, right? But you can answer these questions also by string lookup, right? So we wanted to go beyond that, right? That the question should not be simply a string lookup. And in the definition of educationally useful questions, we said, well, the question has to be pedagogically useful, and it has to be Google hard. Google hard in the sense it's not a string lookup. You have to do more calculation, more computation to answer this question. And it should not also be too hard, right? Because answering any question about a biology book, it's an open-ended research problem, but it should be such that we should be able to solve it in a short amount of time. So we came up with these 5 categories of educationally useful questions. And in this case, we here means teachers and students from a focus group that we had convened. And they gave us 100, 200 or so questions. And then we sort of sat down and we categorized them into these 5 different categories. How do you relate structure to function? How do you perform qualitative comparisons? How do you do similarity reasoning? How do you understand the impact of changing the structure of something on its function? Okay. And we can sort of look at some examples. So for example, if the loop of Henle gets longer, how will its function be impacted? Okay, so let's say we want to answer that question. All right, so this was sort of a set of requirements. So working from this set of requirements, we came up with a vocabulary or a set of relation definitions which should be present in our knowledge graph. And we made this list. And from this, you can see some of them are purely meronymic in nature, where we are modeling the structure of things. There are some relations which are spatial. There are some relations which are about properties. And we had a similar set of relationships for functions, but just to keep the talk scoped, I'm going to primarily focus on the structure relations, because that is enough to give you the sense for the complexity of the problem and the challenge that one faces in doing relation extraction. So then we spent a lot of time trying to come up with definitions for what these actually mean. And this set of definition, which I also sometimes like to call it like a flowchart, may seem a little esoteric, but there is a lot of thought and a lot of literature behind this, based on which we came up with. And the interesting connection between this sort of piece of ontology research with information extraction is that this is the source for our weak labeling functions, right? And when we do the relation extraction in a few slides, and when we are looking for what should be in our weak labeling functions, this is one place where you could get them from. Okay, so let me sort of quickly walk you through this logic. We have 5 relations: has part, element, material, possesses, and has region, right? And we can have any of these 5 relationships between 2 entities if it makes sense to say X has Y in English, right? If it doesn't make sense to say X has Y in English, then none of these relationships quite likely would apply. We would say X has region Y if Y is a region of space defined in relation to X, and it does not make sense to associate Y with properties such as mass or density. Okay, and an everyday example of this would be, let's say you have a table and you want to say, define a relationship between tabletop and table, right? And tabletop is a region of space which is defined in relation to a table. And tabletop by itself doesn't have mass or density. Table does have mass and density, but tabletop doesn't. It's just a region of space. We say X has material Y if Y is tangible and is pervasive in X. Now, continuing with the table example, wood would be material for table because wood is a table is could be made of wood. X has element Y if X is a set of entities of the same type or sibling types that Y is an instance of. Now here the more common example would be like if you have a DNA strand where DNA strand is made of a set of nucleotides, or you in more common sense world, you have a necklace and you have a set of beads which constitute a necklace. So there the relationship between the necklace and the beads is the element relationship. X possesses Y only if Y is energy, bond, or gradient. Now, you may say, oh, this is sort of very strange way of defining it, but this is actually an example application of what Marty Hurst argues, right? So we had this possesses relationship and we went into the book and we see where they were using the possesses relationship, and we tried to look for a generic pattern that we could specify when X possesses Y. And at least for the biology book, this is the best we could come up with, that they were using the word possesses whenever the entities happen to be energy, bond, or gradients. Okay, and if none of these relations applies, then the likely candidate is the Hess-Part relationship. Okay, so I think this is the sort of semantic definition work, which really distinguishes the knowledge graph relation extraction from open information extraction. Where in open information extraction, you don't do this kind of work. You just see what's in the text and that becomes your relation. Okay, but here we are trying to pay attention to what these relations mean, how they are actually used, and how we might be able to axiomatize them, how we might be able to draw conclusions from them. Okay, so having set up that framework and the problem definition, let's now talk about entity extraction and how we can take entity extraction techniques from the first part of the lecture to solve the problem we have here. So we go back to our sentence, and given this sentence, we want to extract plasma membrane, carbohydrate, side chain, proteins, and lipids. Okay, that's what we want to get out of this. Then the first question you would obviously ask is, well, where are we going to get the training data from? And our answer was, well, the textbooks have glossaries at the back. The author has already gone through the pain of figuring out what the key entities are, and they have made a list. That's our training data. Now, that's actually not a bad idea, and actually a good idea. The only problem is that the glossaries, they tend to be not very complete. They don't have everything that you want to extract from these sentences for your knowledge graph. But hey, it's available for free. You don't have to do any work. So why not use it? So that's what we did. So what we did was we found about half a dozen different open source textbooks. We processed them and we extracted the glossaries, and then we fed them into a language model. It's BERT. We were using BERT. We first trained BERT on these books. We did a domain task independent training of BERT on these books. And then we fed these glossaries into the language model. And then we obviously had a dev set and the test set, right? In the development set, we had these about less than a dozen or so books on different topics: physics, psychology, microbiology, chemistry, etc. And then we had a dev set and the test set. And in the test, we were feeding it sentences such as the one you see above here, all cells have cell membranes, but only some have cell walls. And we were expecting it to give us the sentence of the kind you see at the bottom, where it has to tell us the entities, cells, cell membrane, and cell walls. Okay, because that's going to be the first step that we are going to need to build our knowledge graph. So we tested this out, and we found that the precision on this was not bad. I mean, it was 0.67. I'm saying not bad because it's not 0.2 or 0.1, but it's certainly not 0.99 of the kind that we would like to have in the book. And the recall was even lower. It was 0.51. So, I mean, it was missing out on a lot of things you would want to extract. But the beautiful thing about this was that, okay, this is all automatic. You can do this, once you have the code, you could do this right away. And at this point, you would ask, okay, why is it not behaving better? And if you wanted to make it better, how would we go about making it better? So one sort of challenge that we saw, and I mentioned in the previous part of the lecture, was that there are multiple ways to refer to entities, right? So you could have DNA, and then DNA is also same as deoxyribose nuclease, right? And you have to somehow, you either have to have a language model that tells you synonyms, right? Or if you don't have that, and if you just have entity extraction, then entity extractor will think that these are two separate entities, right? And similarly, you may have situations like in a sentence where they are using membrane, in another sentence where they're using cell membrane, but they're talking about the same thing. And then you have to be able to disambiguate between the two. In biology, there are also a lot of unusual plurals. So you have things like mitochondrion versus mitochondria. So mitochondria is the plural form of mitochondrion, but it's a kind of unusual plural. And unless language model knows that, or unless you train your language model for plural detection, it's going to treat these as two separate entities, right? So I think one big lesson that we learned in this whole exercise was that a good lexicon is actually essential if you're going to do very high fidelity term extraction. If you don't have this lexical knowledge, or you train your language model to actually learn the lexicon also, unless you do that, the fidelity of information you're going to get through these language models is not going to be very satisfying to the domain experts. Okay, domain experts of the sort who are writing a book. Okay, I should sort of make that clear. And I think the other thing you would have observed by now is that this relation extraction problem is very different from the relation extraction problem I talked about in the first segment, where we had basically people, places, companies, dates. There are 4 or 5 classes of entities that we were trying to extract. And here the entities are much more varied, and just even the definition of what counts as an entity is sort of very different from what we tend to see in the conventional relation extraction task. So for example, the biologist would consider faulty tumor suppressor gene as an entity, and then the question is, really, is that an entity? And this kind of entity, it's unlikely to exist in a very general language model. It's very peculiar to biology. And then something like control of blood flow to skin, which is a very reasonable function that you may want to have in your knowledge graph. But this is a phrase which is 6 words long, and doing it using language models, it's currently outside the reach of the current language models. And I had briefly mentioned these very general words like attach and synthesis, which you want to identify as nodes in your knowledge graph, which the current systems, they won't obviously do. All right. So given that, let's now move on to the task of relation extraction. Assuming we can do these entities, and maybe we can do the correction. Let's see if we can extract some of the relations we are interested in through these automatic methods. Now, let's go back to the sentence we were working with. We have the entities as shown at the top. We have relations as shown at the bottom. We've identified here that plasma membrane has part carbohydrate side chain, and because they are connected, then they must be abutting each other. So we are using one meronymic and one spatial relationship. Now, the first question that obviously arises here is, where do we get the training data from? Now, in this case, we had some training data we could get from the existing knowledge base, because we had a knowledge base we had hand built. And there is this distance supervision technique using which you can if you already know some relations, you can map them to the textbook sentences. And in addition, we use the weak supervision technique of Chris Ray style, based on the semantic definitions of these relationships that I had alluded to earlier. So essentially, the way the weak supervision works is we define a set of label functions. We apply each of these label functions to every training instance that we have in our input. And then we aggregate the input that these labeling functions are giving us into hard labels and soft labels. Hard labels are obtained based on the majority labels, and soft labels, they are labels calculated by some probabilistic combination of how much we trust each of these labeling functions. And then we have a very similar pipeline where we have the entities from our entity extraction step. We enumerate all pairs of entities, and then we input them into our model. We train that model based on our pre-existing knowledge base and the weak labeling functions. And the task of the model is to tell us what might be the likely relationship between the two entities that appear in a sentence. Okay, so that was the process. Again, the precision turned out to be in the range of 0.65, and recall was in the range of 0.54. I mean, it misses out on a lot of things, but a lot of things that it finds, they are not too bad. It's not like 10% or 20% accuracy, but it's also not 100% or 99%. Now, at this point, the vision that a lot of people get very excited is that, well, you want to feed these books into these learning models and then get the entities and then feed those entities into a second language model, and then you get the relations, and then voila, you'll get these knowledge graphs at the other end. People get excited about that, but because the precision and recall is not quite there, this rosy picture doesn't quite pan out in practice. I don't think it's going to pan out anytime soon. So the picture that I sort of think how these technologies can be used for knowledge graph, highly accurate knowledge graph construction, is to introduce a human review step. So you do some automatic term extraction, and then you have a human actually look at what the model did, and then you feed that into relation extraction. Then you have a human look at it, and then there is this still undefined task of how do you take these triple level information and you sort of synthesize and fuse them or integrate them into a coherent knowledge graph. You could also ask this question, who is going to do the human review? And the vision and the picture that I've been arguing for a while is that, well, this should actually be done by the textbook author. And it should just become part of the process of writing a book, that as you write the book, you process it through these tools, and it gives you some useful information which will also help you improve the book. And yeah, I mean, again, I think the people are sort of receptive to that idea, but I think the thing that I try to do is to see, we need some kind of a futuristic glossary editor and a diagram editor. And this glossary editor gives you a way to bootstrap your glossary at the back of the book in a very comprehensive and text-rooted manner. And this diagram editor lets you visualize every single concept in the book. Okay, and then people start saying that, well, author is never going to do this, and well, maybe there needs to be an author assistant, a new kind of professional who works with the author and who is in charge of doing this kind of processing. Whether somebody is going to buy into this kind of vision, that's still open to discussion. But this is sort of how I think these automated extraction technologies can potentially enable the authoring of highly accurate knowledge graphs. So to summarize, what I've tried to argue in this lecture is that entity extraction and relation extraction, they are sort of fundamental building blocks for creating knowledge graphs from text. At least in sort of my version of the problem, the rule-based methods or methods which start from the semantics of the relation and their potential axiomatic definitions, that's really the place where we start from. And we can use them for generating some training data, and we can feed them into automatic methods. And that, I think, is already popular paradigm. But sort of my own personal take on this is to bring in sort of more semantic definition from the ontology research and knowledge graph side of things, so that what we are actually learning are things that we can do principled inference with. And finally, just to acknowledge, entity linking and entity resolution, they eventually will play a big role in our ability to create these knowledge graphs. As we're still struggling with doing well on the more primitive tasks of entity extraction and relation extraction, I'm expecting that entity resolution in a few years might become an equally important building block. Eventually, we will get there, but with the current state of the art, I don't think we are quite there yet. With that, I'd like to conclude my lecture here, and we still have 7 minutes left for any questions.
Cool, Vinay. So sorry I joined late, but I can see a few questions here.
Okay.
On the Q&A tab.
Okay, go ahead.
So first question is, could you mention again the author of approximate labeling function, please?
Yeah.
Do you recommend any specific paper to read about the labeling for knowledge graphs using ML?
Okay. So the specific author is Chris Ray. And Chris Ray, he gave a lecture in our seminar last year. So if you see our series from last year, I think it was the second session where he talked about Snorkel and his weak labeling approach. So that's the technology we were using for this project.
Okay, thank you. So the next question, could we have a link to the code, maybe in GitHub or somewhere, to try the labeling process?
Yeah, so I think Snorkel has become a commercial product now. I think So, and I think if you send me email, I can send you a link to the code that we developed, which is in public open source. So just send me an email. I can provide a reference.
Yeah, so I have come across several open source projects in GitHub.
Okay.
So search for NLP labeling, and there are a couple of projects actually in that. There's an open source project called Spacey, and they have a new tool called Prodigy, which helps you label stuff also. So that also works quite well. So there are quite a few examples. And the last question here that I see is, are you using predicates such as has part, has function, and function from already published ontologies, or are you defining them internal to your system?
So I'd say a little bit of both. So we actually ourselves have a paper on the semantics of structure and function, which we authored with the partnership with biologists. But as part of that paper, we relate our definitions to what's in the broader ontology research literature. So we are not that different from what people are talking about in the literature. There is certainly some adaptation. Like you might remember, there was one slide in which I explained the flowchart of how you choose between these 5 relations, right? So that actually is based, it's an adaptation of a piece of work that was done by Maria Keat. She is one of the researchers in the ontology research community. So we basically took her framework and then we adapted it, because she was not addressing all the nuances that we were seeing in the book. So I think the short answer is yes, what we're doing is compatible, but I think we've also made some novel contribution to extending what is already known about how to define the semantics of these structure and function relationships.
Cool, thank you. And one question just popped up in the last few seconds. So this is a question about KG validation. Should it be done manually or done by experts? Do you know of any systematic and automatic ways for doing that?
So I think KG validation, I view this as a research problem. I don't think it is solved. I mean, again, I think the doing it in a manual way is a starting point. But I think the way I think about this problem in the context of the intelligent book that we were building was that once you have the KG, then you ought to be able to pose lots and lots of questions to the KG, and you ought to be able to show the answers to an expert. An expert should be able to validate those answers. That's sort of how we were doing the process. But I think once you have that framework in place, there's no reason why you could not put it on a crowdsourcing platform where you have multiple students rating the answer or multiple teachers rating the answers, so that the cost of actually doing the validation is not part of your project. You can somehow sort of farm it out to the crowd platform, right? But it's I don't think it has been worked out, and it's open research.
Okay. And on a related question, related topic, I have a question. In your project, did you use any implicit feedback mechanisms for validation, like Google will collect your clicks and then validate a lot of their algorithm? Anything you did on the students, like measured what they clicked on or something like that?
Yeah, we don't have that. We did not do that yet.
So you did not capture, you capture the clicks and engagement?
We have the capture of the clicks, but okay. We have not utilized it.
Okay. In any way. So yeah, I think that's it on the questions here.
There was something in the chat. Do you use a GraphDB? Which GraphDB is recommended? While we were using at the time what you can call it a logic programming system, that's sort of what we have in the guts of the current prototype. And if we were to ever rebuild it, it would be some version of that. In terms of which GraphDB you recommend, Naren has been planning a lecture towards the end of the series where he will give us a sort of survey of the tools available and what people should consider looking at. So I think we should defer that question to that lecture.
Sounds good. I will keep this question in mind when I present that. Cool. I think we're done, Vinay.
Okay. Mike, do you have anything to add?
No, I don't think so. Unless you want to have a long drawn out argument about rule-based versus machine learning or intelligent textbooks and what exactly they are. But I'm just impressed with how cool the tool that you built is. And I would like it to see it go farther, but I'm happy to see that it's gotten as far as it has.
All right. Well, that's a great closing statement. Thank you, Mike, for your support and inspiration. And I will conclude, and we will continue our series on Thursday On Thursday, we have two fantastic speakers, Aditya Kalyanpur, who worked on the team that had built the Jeopardy system at IBM. He will be talking about his current work on creating causal graphs for understanding natural language. And we will have a second speaker, Ranjay Krishna, who defended his PhD thesis on Friday. He will be talking about how he has been using scene graphs for image understanding. So we will see you on Thursday. Thank you very much.
Bye-bye.